Okay, we're back after a considerable break. So we're going to be starting a new topic. In some sense, most of the time when people think of pseudorandomness, they're mostly thinking about pseudorandom generators. But everything that we have seen so far will just be tools that will be useful in constructing these PRGs and so on. And I'll also tell you some spoiler before that. I mean, there's always this quest of trying to find pseudorandom objects and so on. And this is the only object we have so far not been able to find. Every other thing, like for example, you would like to find expanders, so we find expanders. We manage to construct explicit things. This still, at least in the most general form, still remains an unattained goal. But we will try to make progress towards it and see exactly where we fall behind, and that's going to be the part of this last section of this.
But you have to make clear what you mean by pseudorandom.
Yeah.
Expanders are also pseudorandom.
No, pseudorandom generators.
Oh, pseudorandom generators.
So now we are going to move into pseudorandom generators, and there, like, there are special cases where we know what to do, but the general thing remains. Okay, so let me just do a brief recap of what were pseudorandom objects. Basically, this was a rather vague notion, and it was sort of very tailored to the situation you have at hand. But in a very, very vague sense, the idea that we were trying to build over was the fact that random objects satisfy certain properties, which for us seem very desirable. And we would like to find objects that share these properties that random objects have. I mean, in some situations, maybe random objects are already good enough, so that you can just work with them. But there are several situations where you can imagine that you want some other construction, something that you can get your hands on, something maybe more explicit and so on. But it shares a particular property of random objects that we would like to have. And that's what we have been seeing in various guises, or rather various instantiations of what we mean by what is a property we care about and how we are going to construct them and so on. Okay, and all of these examples, which are like hash functions, expanders, and expanders, we already saw like some 3-4 kinds of expanders, and error correcting codes. And even error correcting codes, you can say, do you want it to be list decodable? Do you want it to be list recoverable, etc. For most reasonable definitions you could come up with, you will have this thing that if you pick an object at random, it will satisfy the property you care about. And in fact, this often, we were using this as a heuristic to sort of get a sense of what sort of quality should we be hoping for. Like, for example, when we are trying to build codes and we wanted to say, I want to achieve very good rate, we usually use the random construction as a guide to sort of say what rate should you be hoping to achieve. Okay, and so it's not just like the base case of do these objects exist, but it often guides you into giving you a heuristic sense of what sort of parameters should you be hoping for. Okay, and so today we are going to be looking at pseudorandom generators, and this is going to be a slightly different notion compared to all the previous notions, because somehow all the previous notions were very combinatorial in nature. There was nothing really computational besides us saying that I want to be able to compute them efficiently. But the definition of the thing that you care about didn't really care about computation as such. It was like some graphs that have certain properties. Eventually, that's what we tried to get to. PRGs is going to be the first instance when the fact that you're dealing with computational things is going to become very rare. Okay. So a use case typically for when you want to use a PRG is something like this. Like you have some algorithm A. Okay. When this is some randomized algorithm, it seems to be using some random bits. And you have some performance guarantee if this algorithm is given completely pure random bits. Okay. And what we would like is we would like similar guarantees without the use of randomness, or maybe with like using less randomness. So that's what we would like to achieve. And it really depends on what type of an algorithm you're dealing with. Because many times, depending on what this algorithm is doing, you might tailor your whatever random bits accordingly. Like for example, something that we saw very early on was that if your algorithm turned out to be very local, like in the sense of the max cut algorithm, there was a stupid randomized algorithm which we had, which like for every vertex we decided to put it either in this side of the cut or that side of the cut. And even though the algorithm seems to be doing something for all vertices, we noticed that the analysis of the algorithm was very local. It really just cared about what happens on one edge. And that one edge only cares about 2 random bits. And when you are dealing with situations like that, and you have some sort of a very local property that is going on, somehow limited independence feels like the right thing that you want to try. Okay. And then there are other situations where your algorithm is doing some form of sampling. Like it's going to pick things at random and you're somehow hoping to sort of say that it's very unlikely for me to be within a small set too often, or some notion of that sort. I'm being very vague here. And in situations like that sort, you might sort of say, oh, rather than using completely uniform random bits to pick subsequent tries, maybe you can do something like an expander random walk. Okay, so some of expander random walks are very good from sort of sampling perspectives. They were great samplers, and the standard Chernoff bounds, etc., continue to hold even if you make your subsequent random bits correlated via expanders. So that was some situation that we have, and the general spirit that I want to convey here is that many times when you want to say, I have an algorithm A, and I want to de-randomize the algorithm, or I want to reduce the randomness of the algorithm, this process is very tailored to what sort of an algorithm it is. So oftentimes you want to look at the algorithm, you want to say that, oh, this algorithm is of a very simplistic nature. And as far as the simplistic nature is concerned, maybe I have different ways of somehow fooling it into thinking that I'm giving fresh randomness. And that's going to be the spirit of PRGs in general. And to begin the discussion, I first need to define a notion of what is called computational indistinguishability. And this is a fundamental notion that is going to be there throughout PRGs. And this is the point where the underlying computational model is already going to become very crucial in the definition. Previously, when we were saying things, it was a purely mathematical, like, or a combinatorial definition that we have. But here it's going to truly depend on what sort of things you are fighting against. Okay, just to be precise, we'll say 2 random variables, x and y, and let's for the moment assume that they are taking, I don't know, values in some domain, capital N. Okay. By the way, we'll use the same thing that whenever I mean capital N, we'll think of it as 0, 1 to the small n. There'll be, okay, so that's the thing that we have. And I want to say that these 2 random variables are epsilon computationally indistinguishable as far as a particular class of tests are concerned. So there's a particular class of tests I'm interested in. Okay. And typically you think of this test as, you think of bounded real value tests. So let's say, for just to normalize things, we'll sort of say that it's something that takes an element in your domain and spits out some number between -1 and 1. That's what your test does. Or if it is convenient for you, you can just think of this test as being a purely Boolean thing. Some of the things it accepts, some of the things it doesn't accept. Just 0 and 1. But let's say we have something like this. And we will say that these 2 random variables are indistinguishable for this class of tests if the following happens, which is you pick any test function in this class and look at the expected behavior when you feed it a random variable, feed it x, and the expected behavior when you feed it 1. And you want these 2 to be very close to each other. So in some sense, this is like going to be epsilon. Okay. So this is what computational indistinguishability is. Just to sort of connect back to something we had seen earlier with respect to expander walks. If you replace this class of tests by all functions, all possible functions from n to -1, 1, what would this computational distinguishability then refer to? That is a notion we had actually seen earlier.
Replacing what by what?
So right now, C is some specific class of test. That is, it's like you tell you it's that I'm only interested in certain things. But suppose you say, no, I'm interested in all tests. Like let C be the class of all possible functions from n to -1, 1. And you're asking, I want to make sure that the expected behavior with respect to random variable x and random variable y, I want them to be roughly the same. So this is basically what we were calling total variation distance or statistical distance. So statistical distance is distance where you want to say with respect to any test you could come up with, these 2 distributions should behave like very simple. Whereas computational indistinguishability is saying, look, I'm not really fighting against all possible tests. Maybe I have a particular class of tests I care about. And I want, under those sort of tests, I want these 2 distributions to be roughly simple. Okay, so that's the distinction that you have between computational indistinguishability and statistical indistinguishability. In which case, if you just replace the class C by the set of all possible functions from n to -1,
Sorry, it's like what I was getting a little this thing about. For that, it suffices to just say T is all test. I mean, T is a Boolean function.
yeah, Boolean is in.
-1 interval somehow
It doesn't matter because
no, I know it doesn't matter, it involves,
yeah.
but somehow that's what prevents
Yeah.
it from
Oh, okay.
making the
Okay.
correction.
So had I instead made it, let's say 0,1 here.
That because I was thinking.
Okay. But it doesn't matter. But the point is, that's the difference between what we saw earlier, where that is like saying, it's like the L1 distribution.
No, not just 0, 1, but more important.
Like the set 0, set 0,1. Yeah. So if you did that, I mean, like
those are special cases.
Yeah, those are special cases of this. But here you can imagine that like maybe two distributions, their statistical distance is actually large because there's a very complicated test that is able to tell apart X and Y. But most of the time we are going to be saying, hey, look, we are running a simple algorithm. There is a very like polynomial time algorithm or something that we are running. I don't really care if there is an exponential time algorithm that can tell these two distributions apart. Maybe I only care about the sort of algorithm I'm fighting against. Okay, so
that's one might be called statistical indistinguishability.
Yeah, that one, in fact, when you replace the C by the set of all possible functions, that is called statistical indistinguishability because this distance is exactly the statistical distance between those two random variables.
So I thought that if you want epsilon to be like extremely small or something, then it's then you can't expect then you can't expect coefficient indistinguishability.
Yeah.
I mean, there seems to be two sort of like you can talk about different epsilon, then you can talk about different class of
different C's. Yeah.
And
so okay, so just think of epsilon as being 0.001 or something. Okay, so some constant. In fact, the example that we're going to look at, epsilon is often said to be like 1/8 or something like that. Okay, so fix some epsilon. And now there's a question of what sort of classes you are fighting against. So if you want to somehow be able to fight against a set of all possible functions, then in some sense X and Y will be computationally indistinguishable if and only if their total variation distance is at most epsilon. But on the other hand, if you care about a specific class of functions, you could get away with X and Y being statistical, like the total variation distance being very large, but computationally you can't really tell them apart. So that's the distinction we are trying to make here. Okay, and so one thing I want to sort of say is that this you should sort of think of this as saying, as far as the tests in C are concerned, X and Y look similar. Like the behavior on X and the behavior on Y is basically the same. Okay, so this is the notion of computational indistinguishability. And once we have this notion, we can now define what pseudorandom generators are. Okay, a pseudorandom generator, again, even that you define it for a class C. It's a definition that you need to first specify what class it is a generator against. So fix a class C. Okay, and you say that something is a generator. A generator is, you often think of it as a map from a certain seed space to your domain. So you have a set of seeds, possible seeds that you have, which is typically much smaller than the domain size. And it's some function that basically takes a seed and spits out something in your domain. Okay, and we will say that is an epsilon PRG if the following two random variables are computationally indistinguishable with respect to C. Which two random variables? The first random variable, so you just give a uniformly random element in the domain. That's random variable 1. Random variable 2, you pick a uniformly random element from the seed space, apply the generator, that's the second random variable. And you want to say that these two distributions should look computationally, it should be computationally indistinguishable as far as the test class C is concerned. That's what a PRG is. So you'll say something is a PRG for a class C if blah 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 this happens. Okay, so I hope the definition is clear. It's basically you want to say that rather than giving these tests uniformly random bits, you would like to instead pick a uniformly random seed, hopefully stretch it using the generator and use that as your random. Okay, so that's what you're hoping to do, and you want some performance guarantees that you could have. Essentially, if the test had an expectation of some, I don't know, half, I am okay if my new expectation is like half plus minus epsilon, but I don't want to deviate more than that. All right. Okay. So now that we have the definition, let's look at an ideal situation. This is what would we like? I mean, we have come up with some definition. What are properties that we would want from these generators, like qualitatively? Okay. So the first thing is, I want whatever this circuit class C that I'm dealing with to be as general as possible. Because I would like to fool larger and larger classes of things. I want to fool more and more complicated tests. Okay, so that's the first kind of whatever aim that we could try to come up with generators that are really general. Okay. The second thing, which is actually going to be quite important, is that I would really like the seed length to be way smaller than. Well, if the seed length was equal to n, this is completely trivial because your generator could just be the identity. Okay, so the whole thing will be interesting only when the seed space is significantly smaller than the domain space. Okay, and the third thing I would want is that, I mean, eventually speaking, if you want to use this generator to de-randomize algorithm, there should be some notion of efficiency that you have for this generator also. Like, there are two notions of efficiency that you have. Maybe first you want to find this function g, whatever you're going to do. And secondly, at a seed, you want to evaluate the function to figure out what is the seed getting evaluated. So there are two notions of efficiency that you actually have to deal with. Okay, there's a notion of finding this function and there's a notion of actually evaluating this function. Okay, so I'm just going to spell out a few things, but these are like details you just keep track of once and then you sort of forget about it. Which is, normally speaking, when you're talking about generators, I shouldn't give you a single generator, I should actually give you a family. Like there should be like one for every length, because just like you have algorithms will be running on inputs of many different lengths. So you typically think of a generator as a sequence of functions or a family of functions, maybe indexed by what sort of domain you're dealing with. You want a generator that eventually stretches to n bits, okay, that is the generator Gn. Okay, and maybe in order for you to stretch to n bits, you need to have a seed length of, I don't know, dn or something. Okay, you need to set this up, and now there is a notion of what do you mean by you find this generator. So the finding the generator could be like, if someone, suppose you come and tell me that, I need a generator that is able to handle 2000 bit inputs. Now I need to figure out what is the seed length for that 2000. So there should be some algorithm that when fed 2000 tells me, oh, by the way, the seed length is 35 or something. Okay. And similarly, I now say, look, I want to evaluate the 35th generator on a string y. I want to be able to do that efficiently. So you just tell yourself that you are expecting polynomial time algorithms to do these things. That's what your notion of efficiency is.
So right now, we are trying to, let's say, de-randomize certain class of algorithms, and we want to say, okay, just for this class of algorithms, I want to somehow use as few random bits as possible so that I can still generate like n bits of randomness or whatever I need, so that for that class of algorithm, it's good enough.
Yeah.
I mean, it feels like, okay, PRGs, like, I guess we don't have the most general PRGs right now and so on. It feels like the sort of easy, like a weaker thing that one would have wanted is the definition for a like computing PRG also includes not just the input, the number of bits you are trying to generate, but also a description for a specific algorithm that you're trying to fool.
So that somehow I am hoping that the class C is somehow encoding it inside. Like the class C is what is telling you what sort of algorithms you're trying to fool. Like for instance, things like this we are already doing. Like if you recall what we did for samplers, for instance, suppose your class C was the following class of functions. It's going to pick random points and just evaluate the function on those random points. Suppose that's what your class C does. Now the generator were exactly your hash functions or samplers or something, because you used a small number of random bits to generate these samples in such a way that even if I didn't give it completely uniform samples, the empirical average was close to the actual average. So we were doing it in some regard, but now I'm just stating it for a general class of tests that you may care. Okay. So our notion of efficiency therefore is basically going to be, I want it to be T computable, to basically mean that the sort of things you care about are quickly computable. That is, given the output length, I need to know what sort of seed length I should be dealing with, and I should be able to evaluate on any seed relatively quickly. Okay. So this is the notion of efficiency that we care about. It's a natural notion of efficiency. Don't worry too much about the details of exactly what happens. Just some reasonable way in which you can say these can be. Okay. So the first thing is I want to start is to say why would PRGs be helpful? So the first thing is I want to say that this is a very simple theorem, which is that if you have good PRGs that are efficient, you immediately have de-randomization. Okay, and I'm trying to state this in the most general form, but we will then water down based on what is.
Why 8?
Oh, 1 by 8.
Oh, sorry. Yeah.
Sorry. Yeah. So I meant, yeah, 1 by 8. That still looks like a y to me now. Now that you point it. Yeah. Okay, fine. I can't answer
it. Once you latch on to that, then it's a fancy.
So there is a joke about somebody who had some class, some math class where someone at the end of it said, "No, I don't understand this notation, which is this, the mirror image of a capital D." Then this person was like, "What? You're looking all over the board." And then it turned out it was the complex numbers. Anyway, so let's look at the ideal situation of what we would want for PRGs. Okay, which is like maybe your class of functions are basically anything computable by Boolean circuits of size n squared. Maybe that's my class. Okay. And suppose by some miracle, we manage to find a pseudorandom generator, which is like a 1 by 8 pseudorandom generator. The epsilon is set to 1 by 8. And there is some function dn as a function of n, right? Which is the seed length in comparison to what you want to get. If you're able to do that, you immediately have that the set of all randomized bounded error probabilistic algorithms, okay, they can be de-randomized in roughly this much time. Okay, it's sort of good to keep track of one useful thing where suppose d of n, this turns out to be order log n. Okay, and suppose it turns out that t of n is basically polygon n. That is, it's polynomial time computable, and the seed length is like logarithmic in the final stretch that you want.
Okay, just make
because
so you're saying d subscript n there. So
oh, sorry. What I meant is this is some function d of n.
No, I get that.
Yeah. Okay. So suppose this was the sort of parameters you have for your generator. That is, somehow your generator takes a seed of length order log n, manages to stretch it to n somehow. Okay, and it happens to just make the error just 1 by 8. If you plug this into what you have on the right hand side, d of n power c will also be like order log n. For any constant c, it will again be order log n. Okay, so therefore 2 to the d of n power c is going to be polynomial in n, and everything here is also polynomial. So it means that this tells you that anything that can be done in probabilistic polynomial time can actually be done in deterministic polynomial. So it will basically tell you that you can completely de-randomize BP. Okay, that is of course assuming that we find generators that have this sort of guarantee. Okay, so the proof of these things are not hard, but it's just setting up the right language that is needed. So let's say A is some randomized algorithm. For some language L in BPP. Okay, and and suppose A runs in, I don't know, some n to the c time. I'll give this a name. Let me call this M from now on. Okay. So what does this mean? This means that for every string X is in the language. If X is in the language, the following holds. Probability over the random choices of A, that A of X comma R accepts. I want this to be at least 2/3. And if X is not in the language, I want the same probability. I want this to be at most 1/3. Okay. And since I'm assuming that A runs in time at most n to the c, the largest number of random bits it can use is at most going to be like n to the c. So we can just say that A uses at most m random bits. On an n length input. Okay. So now I want to somehow give you a new A is solving the problem L that we care about. It's like doing membership for L, but of course A is a randomized. What I want to do is build a deterministic algorithm that still solves membership in. So let me just give you a new algorithm. The new algo, which I'll call B. The input to this algorithm is again just X. Okay. So here's what it does. First thing it does is compute this generator GM, which is something that is going to take 0, 1 to the D of M to 0, 1 to the M. Okay. By compute, I mean figure out what D of M is and then have some description of that. The next thing I want to do is compute alpha, which is going to be the expectation where you draw Z uniformly at random from D of M, and then you run A on X comma, what should I do? GM of Z. Okay. And by this, when I say compute this expectation, you literally go over every single thing in the seed, figure out the fraction of points at which A ends up accepting and not accepting. Okay, and I'm just going to say accept if alpha is greater than half, reject otherwise. Okay, so that's going to be the new algorithm. This is right now a completely deterministic algorithm. There is no randomness used. This expectation is written there just for shorthand. You just run over all the things. And notice that from this algorithm, it's automatically clear that the running time is what was claimed here. Because how many seeds do I need to run over? I need to run over 2 to the D of M possible Zs. And M was like n to the C. So it's like 2 to the D of n to the C. So that's the number of times I need to do this computation. And for every such computation, I will have to run my old algorithm and also maybe compute the seed at that particular point. So that's what this basically says. So this is like 2 to the this many times I need to do this computation. So that's the total time that we ended up taking.
And also here is how much to compute the generator. Right?
So I'm assuming that is all within this T of n to the C. I'm saying that the generator is T computable. So that's how much time that this takes. Okay. But okay, so all this is fine. But the point is, what is this thing that you're full? We started out with the BPP algorithm A, but the generator is only supposed to fool circuits of size like n squared. Okay. Now, where do these circuits of size n squared come? And so the point is, suppose you just imagine that you have this new algorithm A prime, which the only thing it does is take a random bit, and then what it returns is just A of X comma R. It's like it just runs the previous algorithm where you are sort of hard-coded this input X, and all you're doing is given a random sequence, it tells you what it does on that random sequence. Okay,
X is a fixed input.
X is some fixed input, right? And the only observation that you really need here is that even though A is a randomized algorithm, if you just look at what A prime is doing, it's taking some random bits and making some computation. You can sort of just look at your randomized algorithm, just write it as some circuit of size n squared or something. I'm just being like,
Yeah, I was just because this is basically
this is like Cook-Levin. Basically, it's Cook-Levin.
square, but it's like
It's basically m log m or something. I am just being sloppy and saying m squared is certainly like liberal enough that this will just work. So whatever this A prime is, this A prime is computable by some circuit of size at most n squared. Okay, this goes through the Cook-Levin theorem, and this just take this on faith if you don't recall.
we have Chomsky as a beautiful tool for this.
What is exactly computational?
Huh? Sorry?
Yeah, I'm a little bit lost here. It's probably easy about that one. So what's it?
So A prime, the input X has already been hard coded inside.
Yeah.
The only thing is I give you a random stream and I ask you, what would the original algorithm A have done on this input and this random stream? And that particular description, you can just write the algorithm as a whatever, the Turing machine computation. You can just, the simplest thing I can see is you just write down the tableau and you get an m squared sort of thing. That gives you m squared. If one can be cleverer and get m log n or n log. Okay, so this implies that G, whatever Gm, must sort of fool this A prime of R. Because A prime of R is one of those tests in the class of tests that G is supposed to fool. Because A prime is one of these functions that is computable by circuits of size n squared. And that's what I assume GM is supposed to. GM is supposed to fool any test that is computable by circuits of size n squared. Now let's see what this means. Okay, so this implies that the expectation of A prime of R, where R is chosen uniformly at random, versus the expectation where you choose Z uniformly at random from whatever D of M or something, of A prime of G of Z, maybe it's GM of Z. This difference is at most 1 by 8. Now, if X was in the language, in that case, this value is like at least 2/3. Right, because that was the definition of BPP. This is okay. And if this is at least 2/3 and the difference is supposed to be at most 1 by 8, you immediately have that this better be at least as large as 2 by 3 minus 1 by 8, which I think is 13 by 24. Okay, which is bigger than half. Okay, and on the other hand, if this was less than 1 by 3, which is the no inst, that is, if X was not in the language, then I know that the left-hand side probability would have been at most 1/3. But then this can be no larger than 1 by 3 plus 1 by 8, which is at most 11 by 24, which is also less than half. I mean, this is less than half. So your cutoff for saying that if this alpha turned out to be bigger than half, I will accept is perfectly sane, because in the yes instance, you would have been at least 13 by 24. And in the no instance, you would have been at most 11 by 24. So you're fine. Okay, and whatever, running time bound is the same. So and running time is as claimed. Okay. And that basically completes the proof to sort of say that if you manage to find such amazing pseudorandom generators, this will lead to a complete de-randomization of people. Okay. But in general, this also tells you that, maybe asking for d of n equal to log n is probably like really strong. But you can imagine that if someone told us that, d of n being like, I don't know, n to the epsilon for a very, very small epsilon, that will already start being interesting. So in the sense that, we don't need to be so particular that we would like a log n size field length. But maybe we would take anything that we can get in some sense. Okay, so basically one notion of explicitness, just like all the previous pseudorandom generators that we were thinking of, is you can define this notion of explicitness in the following two forms. When you say someone is supposed to output a generator, what would you want? Do you want someone to just write down the truth table? Or would you want someone to be able to compute one seed at a time? Okay, and depending on that, you can call it a mildly explicit or a strongly explicit sort of thing. This is very similar to all the previous examples that we were looking at. Okay, and in many cases, when you are going to use your pseudorandom generator to do an eventual de-randomization, that is, you are anyway willing to go over all possible seeds in your domain. In many instances, mildly explicit is already good enough because you already told yourself that I'm going to run, there is going to be some 2 to the d of n running time that I'm willing to tolerate because I'm going to go over all possible seeds. And in such situations, mildly explicit would probably be good enough for your whatever analysis you have in mind. Again, there may be some other situations where strongly explicit is perhaps what you want. Okay, so that was what PRGs were and why PRGs were useful. But as always, we should be asking, okay, we would like this amazing object and we would like to construct them. So first thing we ask is, do these objects exist at all? Okay, is it even reasonable to hope for PRGs with this much seed length? And we will see that, yes, there do exist PRGs, but against size and squared circuits, just like the one we wanted in the previous theorem, where the seed length is actually just order log n. And if epsilon is a constant, it's truly order log n. Otherwise, if you care about the epsilon that you're going to be dealing with, it's like order log n plus log 1 over epsilon. Okay. And of course, the important thing here is going to be, these are all going to be non-explicit. Okay. And we are not just going to say that there are PRGs. We'll basically say there are tons of PRGs. So it's yet again going to be one of this finding hay in a haystack type situation. Okay. So let's do this. And again, this must hopefully be sort of standard, Whenever you want to show these sort of objects exist, the first thing you should try and do is just pick this object at random. You want a pseudorandom object, a random object is a pseudorandom object. So let's just pick a function g at random and just see, what sort of parameters will allow us to argue that that random object satisfies the property. Okay, so we'll pick g as a random function. So let's just spell it out. What does this mean? That is for every possible seed, assign an independent uniform y in 0, 1 to the, what did I call it? M as g of c. That is, for every seed, you're just basically assigning a random. And I want to know, is this going to be a good generator? Okay, so now let's do the following. Let's fix a test. Okay, so we are trying to compare the following thing. So let's define mu to be the actual expectation of this test, where this y is chosen uniformly at random. This is the actual expectation of whatever this test has. The next thing I want to know is what would be the expectation had I used the generator. Okay, so that is going to be my mu hat. And what is this going to be? This is basically going to be sum over I going from 1 to, I don't know, 2 to the d or something. The t of g of zi, and maybe I need to divide by 2 to the d. That is, you look at the expectation on all the generator inputs, and this is the same thing because we defined this completely at random. This is 2 to the d times summation t of yi, where I going from 1 to 2 to the d, and each of these yi's were basically uniformly random choices that we ended up picking. Okay, and what I want to point out is that mu hat really looks like you're trying to do an empirical average of what the actual average is. The actual average is basically I need to go over all possible 2 to the n strings. Whereas mu hat is like saying it is picking 2 to the d uniformly random samples and taking the average among those. And what do we want to know? We want to know if I pick 2 power d uniformly random samples and look at the empirical average, how much does it deviate from the actual average? And this is exactly Chernoff. Okay, so the probability that what is this? Mu hat minus mu, this is greater than epsilon. This is at most some exponential in minus epsilon squared times the number of samples you ended up taking. Okay, that's what Chernoff bound tells you. Okay, that the probability that this mu hat deviates from the actual expectation by a lot is like some small quantity. And when this event happens, we will say that G is bad for this test.
Just to make things clear, here Ty is the random variable.
Yeah, Ty is a random variable, and we are taking 2 to the d samples of them, and we are saying that we are comparing that with the actual mu, actual expectation. So, I mean, I'm saying this G is bad because if I had chosen a certain G where this event happened, then T can say, hey, I didn't get fooled because my actual expectation was mu, and you outputted something that was away from me by at least epsilon. Okay, so what we have right now is that probability when I choose G at random, that G is bad for this T. This is at most some exponential in minus epsilon squared 2 power T. Okay, but again, we just chose one such test. We are probably fighting against many things. So what all are we fighting about? So the probability that G is bad for some T, this is at most just by a union bound. This is exponential in minus epsilon squared 2 power D times the number of tests that you're dealing with. Because for every such test, the chance of you being bad is small, and this is just a union bound. And now, and this is actually a very general statement, there was nothing very special about circuits or something. So far, T was some test, and as long as your bag of tests is small, this number is small. And you can now ask, how many different Boolean functions can I have which are computable by circuits of size n squared? Okay, and I'll let you think about this, and this is sort of not hard to see that this is at most exponential in minus epsilon squared 2 power D. A safe bound is something like 2 to the m cube or something. Technically, m squared log m is enough, but I'm just putting m cube here. Okay, and now so far we have not set what D is. Now I want to basically say that if D is reasonable, the probability here you can probably drive down to whatever you can. So this quantity will be much, much smaller than 1 if D is something like, I don't know, if it's something like 4 times log m plus log 1 over epsilon, then this is going to, because this will start contributing at least m power 4 or something, which will kill everything else that we have here. Okay, and so therefore, there are many PRGs for size m squared circuits with seed length something like order log m plus log 1 over epsilon. So going back to the previous theorem, we needed epsilon to be like 1 by 8, and we were hoping for seed length which was like order log m. And this theorem basically says that there do exist such things. Whatever you are looking for, such things do exist. But at the moment, this is a random construction. We would like an explicit. Okay, so are there any questions so far? And that we were dealing with circuits was really not relevant here. The only thing you care about is some way of capturing how many different tests are you dealing with. Now notice that if you deal with a set of all possible tests, the number of set of all possible Boolean functions is 2 power 2 power n. That would be way too large. But as long as you're dealing with some smaller set of tests, you can aim for generators that have smaller sequence. Okay, so that's what they are. So the goal is going to be to construct these explicit PRGs. And as I mentioned earlier, we are not going to be able to do that. But we will try to get as close to it as possible. And when we say we will try to get as close to it as possible, typically in these situations, you try to do something, sometimes you get stuck, you try to ask simpler questions. Now, what are, can we give ourselves smaller goals that we can try to achieve? And since there are several parameters involved and qualitatively there are many things that are here, your notion of a simpler goal could also be very different. Like for example, here are 3 different questions you could ask. Okay, so the first type of question that you could ask is the following, which is, okay, maybe I don't really care about the seed length being logarithmic. I am okay as long as the seed length is some like significantly smaller than the samples, the whatever the domain says. Now maybe I want seed length of just m to the epsilon. Maybe this will result in saying that everything in BPP can be done in deterministic 2 to the n to the 0.1 time or something, which will still be interesting. So maybe that is one thing you could ask for. Okay, so that is one. The other thing you could ask for is, okay, fine, maybe I'm okay with, not having unconditional constructions, but can we say something like, unless some stupid thing like, polynomial time and p-space collapses or something, such generators I can construct or something. I mean, like you say that the only time, like if I assume certain complexity theoretic assumptions, maybe in such cases I can construct generators. Like you give me a hard function, I will tell you how to construct the generators. So that's one of the things that we'll be looking at in the next few lectures. And the third thing you could ask for is the following. Let's start with simpler tests. Eventually, we would like to go to Boolean circuits that are computable by n squared or something. But maybe you start off with really, really simple tests and slowly build your way up to come up with more and more complicated tests. Okay. So, and this is also sort of, it gives us some sense of, what these generators will sort of look like. So let's look at a few of them. So I'm going to give you, okay, here is one such test. This is a class of tests that the bag of functions I care about are what are called dictators. Okay. Every element of this class, it takes a string as input, but it basically returns whatever is present in one location. So the ith dictator is basically to just disregard everything else and just basically return whatever was in the ith. Now suppose this was your class of tests. Can you construct a PRG from this? Okay. And let's repeat. Sorry?
So you just want this class basically just outputting this ith bit.
Every test in this class is outputting that, but of course, this class consists of n different functions. One for every
each.
Yeah.
So
okay.
Your PRG is going to take one random bit and just output a power.
Yeah. So you can sort of think of in fact, if you want to think of it as your distribution is just the following. There is 0, 0, 0 and 1, 1, 1.
Exactly.
Okay, and basically your generator on one thing it returns this, on the other thing it returns this. Of course, the expected behavior is what you want it to be. So here seed length is awesome, seed length is 1, and you're able to stretch 1 to n bits. Okay, great. So the next thing could be the following. That is, you have your class. Previously was a class of functions where every element on your class really depended on just one bit. We said generator, just dictators. You could even add anti-dictators or some nonsense there that would have still worked. So the obvious generalization you could ask for is, suppose your bag of functions is made up of some things where every single test depends on just two coordinates of your input. You don't know which two they depend on, and you don't know how they depend on the two coordinates. There could be some arbitrary function on those two coordinates. So in such situations, what would a generator do? Yeah, these are things that you have already looked at. So what would they be? So if you think of it from the perspective of PRGs, this, yeah, so Yogesh says, yeah, two-wise independent hash functions, exactly. So this basically is perfectly suited for limited independence, right? Like as long as you guarantee that your distribution has a property that any two bits you look at look completely uniform. In fact, it will have zero error. I mean, like when you use that. So here you can just use pairwise independence. Okay. And now comes the next thing, which it's very simple to state, but it's like incredibly powerful. Okay. So this is the class of all linear functions in X. Okay. Formally speaking, this is what the class looks like. So it has the back consists of 2 power n functions, and every function is like you choose a certain subset of coordinates, and you just take the parity of those coordinates. Okay. So it's these are just linear functions. And so even though this is like, it feels like such a simple thing to start with, this is unbelievably useful to have PRGs that are good for this thing. And in this class, in the remaining time, we will see one such construction. But in the next class, I hope to give you applications of this. And the application will look nothing like linearity. It will just work for a whole host of things. Okay. And PRGs for these above classes, I mean, just the class of linear functions, they are called small bias spaces often. Okay. And if you want it to be an epsilon PRG, it's often called an epsilon bias space. Okay. And they're really ubiquitous and they're very useful. And what we are going to be doing in the remaining time is to give one such construction of an epsilon bias space. Okay, and we will see why that. So, but before that, I want to sort of get a sense of that none of the previous constructions will actually give you an epsilon bias space. I just want to say that it's not as easy as we may think it to be. So obviously, this is not an epsilon bias space, because if you take your parity to be x1 and x2 together, well, I mean, you're going to always output 0. So that is bad. And you could now ask, okay, is limited independence sort of enough for epsilon bias? Like, can I somehow cook up with, let's say, maybe not pairwise independence, but maybe some largish independence? Is it reasonable to expect that a largish independence is actually going to be epsilon bias? Okay, and even that is not the case, because you take the following distribution, D. When I mean distribution, I'm going to give you a set of strings, and the distribution is just the uniform distribution on these strings. So this is a set of all x such that summation xi is equal to 0. And by summation xi, I mean mod 2. Okay, so that's what the string is. This is the distribution that is supported on 2 power n minus 1 strings. It's just throwing away half of that. Okay, and it's not hard to see that this is actually n minus 1 independent. Right? This is like an n minus 1 independent distribution because you're completely free to choose n minus 1 coordinates. You just set the last coordinate just so that the parity adds up to parity is 0 or something. But by very construction, if you look at the parity, which is a set of all n bits, that is not full here at all. So this is it is an n minus 1 independent distribution, but not epsilon biased. Okay. And it turns out that epsilon bias is also very useful from the perspective of codes and so on, which I'll try to tell more about in the next lecture. But what I want to describe is a construction, or rather, it's one of the constructions of this paper of Alon, Goldreich, Pastad, and Peralta. Okay. And it again is one of, so this AGHP paper actually has 3 constructions in that paper. It's a super short paper. Each construction is like 1 page long. It's a pleasure to read. And what I'm going to describe is what I believe is the easiest construction among the things that I know. Okay. So good. So here is how the construction is going to work, and it uses the following very simple exercise that is often given. Okay, so here is the lemma that we are going to use, which is suppose x1 through xn. Okay, this is, I'm going to think of this as some vector in f2 to the n. Okay, and let's say it is non-zero. Okay, and I want to know what is the probability that if I pick a vector r at random, I want to know what is the inner product of r and x. That is, you fix a vector x, x is a fixed vector, the only guarantee you have is that it's a non-zero vector. And now you're looking at the following question, which is that I pick a vector r at random, and I ask, what is the chance that the inner product of r and x is actually equal to 0? And inner product is like everything here is over f2. Okay? And this is exactly equal to half. Okay? Obviously, if x was 0, this will always be 0. But the point is, the moment you know x is non-zero, as long as it's, I mean, the only thing you need is that it's not 0, this probability is exactly half. I mean, I don't want to do this proof. I think this is a common exercise question in many places. But this is what we are going to actually end up using. Okay? So here is the AGHP construction. So the first thing you do is you build one of these extension fields. Okay? So you build an extension field of an appropriate size, and I'm going to call this some f2 power, I don't know, k. Okay, maybe k is a bad choice. What do I call this? L. With the basically, I'm going to choose this L such that this is like roughly n over epsilon or something. Okay. So the size of this field is now going to be like n over epsilon. You start with the field f2, which only has 2 elements. But you go to a suitable extension such that your field now is just n over epsilon or something. Okay. And now I'm going to tell you, give you a generator, but instead of giving you a generator, I'll give it to you as a distribution. Okay. So the generator is sort of going to do the following. It's going to take 2 field elements, okay, which I will call A and B, and maps it to the following n-bit string. So the seed space is just 2 field elements. That's my seed space. But now I need to spit out n random bits. Okay, now what am I going to do? I'm going to basically, I'm just going to look at 1 a squared, a power n minus 1. This is one thing I would like to just spit out. 1a, I mean, by a squared, and all these are all elements in the field. So it makes sense for me to square, cube, blah, blah, blah. Okay. But obviously, all of them are now no longer going to be bits. They're going to be large things. Right. And this is where the second vector b is supposed to come in. And notice that this can also be thought of as a vector space over f2. Like every element of the extension is basically an L tuple of things. So you just think of it as a vector space. And you just modify this construction by just taking an inner product with B. So this is going to be the inner product of 1 with B, the inner product of A with B, blah, 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 the inner product of A power n minus 1 with B. Okay? And that is the construction. So once you fix 2 field elements A and B, then you know exactly what are the n bits that you're outputting. Okay, and we're somehow going to show that this distribution is actually, I mean, by distribution, I mean, if you now choose A and B uniformly at random, it will have this epsilon bias property. That's that no matter what parity you have in mind, the parity will be equally biased towards being 0 and 1, or the bias will just be at most epsilon. So is the construction clear? So I'm using some very basic field theory in this. Just that there are extensions that you can construct, and once you construct such an extension, you have just this. Now the question is, why is this small biased? Okay. Now let's fix a parity. In parity. Okay. Now, firstly, notice that if S was empty, I mean, by definition, the empty parity is always going to return 0. Okay. So whether or not, irrespective of what distribution it is going to return 0. So let's focus on just parity being non-empty. Okay. Now, as long as I have a non-empty parity, if I feed it uniformly random bits, this parity will be equally likely.
S for empty.
Oh, so yeah. I'm going to assume that S is non-empty. Okay. Yeah. As long as S is non-empty, in the uniform setting, like the probability that the parity is equal to 0 is exactly equal to half. So therefore, what I want to get a sense of is, under this distribution, what is the probability that I actually end up getting 0? Okay. So what is the probability for this parity being 0? Okay. So this is the standard use of the polynomial method. So I'm going to define a polynomial f of, let me give it a name. So let's say f of z, which is summation z power I, where I belongs to this set S. That is, the parity is choosing a bunch of coordinates. So I'm just thinking of that as a formal polynomial. Okay, where those corresponding monomials have been chosen. Okay. And what do I want to know? I want to know so when I ask for the certain parity, we are basically asking this probability.
You should say this polynomial is over what?
Oh, so this polynomial is over F2. This is over F2Z. Okay. But I'm going to in fact think of this as a polynomial over whatever, this KZ. It's just that the coefficients at the moment happen to only be zeros or ones. But I will try and evaluate this polynomial and things in the extension. Okay. And what do I know about the degree of this polynomial? Well, it's no more than n, because I'm just picking up monomials corresponding to the coordinates, and I have only n coordinates. So the degree is at most n. Okay. What is the parity we care about? We care about the parity of I in S of a power I b. Sorry, b. Right, because this was the ith coordinate of my generator. And that's what we were caring about. And now I can write, because this dot product distributes over sums. So this can be written as summation a power I, where I is in S, and then I take a dot product with B. Because addition is the same thing as coordinate-wide addition, and then dot products just distribute over the sums. And this therefore now has this nice way of, because I have defined this polynomial f, this is the same thing as I'm evaluating the polynomial f at the point A, and then taking a dot product with B. Okay. And now I want to know, what is the chance that this thing is going to be equal to 0? Okay. Instead, let's do the following. Let's ask the chance. What's the chance that it is non-zero? Okay. And this goes back to the previous lemma that we had, which is that once you fix a certain vector, and as long as you guarantee that that vector is non-zero, if you take a random inner product, that is going to be equally likely to be 0 or 1. And the fixed vector I'm going to think of is f of a. I'm going to think of two situations. Either it is the case that f of a actually turns out to be the 0, right? It's the 0 element of the field. or f of a is a non-zero element of the field. I want to ask, if f of a were the zero element, what would happen to this dot product? And if it was a non-zero element, what would happen to this dot product? Okay, so the probability that f of a, comma b, this is equal to 0. This can happen because of two situations. Either it is the case that f of a itself is 0, in which case, of course, the dot product will be 0. Or f of a is non-zero, but somehow the dot product became 0. So this is equal to probability.
So B is a random vector.
Yeah, both A and B are random at the moment. So we're going to split this probability into two situations. One where
a random vector over 0, F2 to the
right.
L.
Yeah, F2 to the L there. So the chance that this is equal to 0, it can either happen because f of a itself was the 0 element of the field K. Okay. Or that I have this inner product of f of a and b, this to be equal to 0, conditioned on the fact that whatever f of a is actually non-zero. Okay, so the probability is at most this quantity, right? And well, what can I say about this? So this, okay, let's look at the second part. The second part, for every fixing such that f of a is non-zero, because b is a uniformly random vector, it is equally likely to be half, or like equally likely to be 0 or 1. So therefore, this probability is actually exactly equal to half.
And this part didn't use the fact that you had chosen it so carefully as 1a square.
Yeah. I could have.
This part is just the randomness of b.
It's just the randomness of b. Now the second part is where I want to say f was some non-zero polynomial. Why was it non-zero? Because I assumed that the parity was a non-empty parity. So therefore, the polynomial is a non-zero polynomial. It has degree at most n. I am choosing a random element a from a field of size n over epsilon. Well, it can have at most n roots. So the chance that I was unlucky and I picked up one of those roots is going to be at most epsilon. So therefore, this is at most epsilon.
This is where you're using the fact that it was chosen as 1a.
Yeah, 1a squared. So therefore, this tells us that the chance that you are actually equal to 0 is at most like half plus epsilon. And the same thing you can turn it around for, you can actually say that, basically the way you should sort of think of this as the following. If fa is non-zero, it is a completely unbiased random variable. So there is a small chance that fa could actually be equal to 0, which could change the bias by something like epsilon, but no. And this basically this is what tells us that therefore, whatever this G is an epsilon biased space, or it's a generator against linear functions. Okay, maybe this part I went a little quickly, but
So I would argue at most against degree n polynomial.
Degree n polynomial, n minus 1 or whatever.
Which
Yeah.
And so your L should be that's why you took K to be.
Yeah, that's why I chose K to be equal to n over epsilon. Where was this K? N over epsilon. So the L is like log of n over epsilon. Okay. Okay, great. So now it's actually whenever you have these generators, it's always a good idea to get a sense of how large is the sample space. So right now this generator G, this is something from, where is it? This is in, what happened? 0, 1 to the 2 log n over epsilon to 0, 1 to the n. That's the current description of this. Okay. If you think about it in terms of just the seed length, that is, it's like going from d to n or something. Okay. This d is like n squared over epsilon squared. Right. Now you could ask, is this the best you could do? Can you actually come up with an even smaller thing? Is n squared over epsilon squared the right answer? Are there even sparser distributions, etc.? Now, it was known for a long time that the right answer is supposed to be n over epsilon squared. Okay, even though AGHP construction gives you an n squared, which at this point it doesn't matter. But I'm just saying that this was a long-standing question saying that can you achieve epsilon bias spaces where the number of strings you have in your distribution is just n over epsilon squared rather than n squared over epsilon squared. And we recently, I mean, like Amnon Tashma managed to get a construction which is very close to this. That is, it really, really approaches this. In the sense that, so there is a construction of Tashma that basically, I think, gets something like n power 1 plus alpha divided by epsilon power 2 minus alpha. And you can choose your alpha the way you want. And the way Tashma manages to construct this is actually using expander random walks.
This was supposed to be really big.
Yeah, this was a major breakthrough. And it uses this something called the wide replacement product to build this thing. And in general, epsilon bias spaces is like is extremely useful in the there are crazy situations where you want to build a generator and you somehow it just so happens that epsilon bias spaces are already good enough. And in the next lecture, what I hope to do is basically give you some examples of it. So one thing that I will say right now, but we will prove it in the next lecture, which is that, so there are many instances. Let's go back to recalling what pairwise independent meant. Pairwise independent meant that, you have some hash function and you're picking a hash function at random and you have two specific inputs that you've already chosen. And you're asking, what's the chance that at this input it took this value and this input it took that value? If it were completely independent, this will be 1 over m squared, where m was the whatever range that you have. And you want to have pairwise independent hash family to actually achieve 1 over m squared. Now you can imagine situations where you don't really care for this being 1 over m squared. You're okay if it was 1 over m squared plus minus epsilon. Okay, so that is, you don't exactly want independence here, but as long as this probability is like 1 over epsilon plus 1 over m squared plus minus epsilon, you're probably okay with this. So these such distributions are called almost pairwise independence. And there is a beautiful construction of almost pairwise independent distribution that just follows epsilon bias spaces. So if you recall how pairwise independent distributions were constructed, we basically chose the coordinates of some low, I don't know, degree 1 or degree 2 polynomial from a field. We chose those things independently and then we evaluated them at various points. It will turn out that instead of choosing them independently, if you choose it according to an epsilon bias space, it will become almost k-wise independent. So those are some of the examples that we will see in the next lecture. And in general, the reason these sort of parities, or rather these linear tests, are so important is for people who have seen Fourier analysis. You can imagine that the whole point of Fourier analysis is to basically decompose your function into the relevant parities that are involved. And therefore, these epsilon bias spaces basically are telling you how to fool every single component of it. And as long as there isn't, you can somehow handle the mixing that is happening, you manage to fool those larger classes. So epsilon bias spaces are really, really powerful. And it's an excellent first example of a simple test that we want to fool. And we will see more examples of it in the next lecture. So what my plan for the next few lectures is basically to maybe give some examples of epsilon bias spaces and its applications, and then basically directly dive into these conditional constructions. So I initially thought I will try and do something like RL versus L sort of thing, but depending on the number of lectures that we have left, I don't know. If I cover that, I will completely miss out on things like Nissan-Wigderson, Impari-Katz-Wigderson and stuff. So since the previous offering has videos of RL versus L type stuff, I thought this time we will do this other thing. Okay.
I have a question.
Uh-huh.
Because I don't remember this paper. So, yeah. Go to this place where you did the analysis. A little bit down.
Here?
No, sorry, go up there. No, there.
Uh-huh.
So this analysis is basically two things have happened, right?
Mm-hmm.
One is, well, V was completely random.
Yeah.
So there M doesn't matter.
Yeah. As long as it's non-zero.
As long as it's non-zero.
Uh-huh.
And therefore, complementarily, what matters is F is some function whose probability of outputting a zero vector is small.
That's right. Exactly.
Now, the other two undescribed constructions of somehow, this is the one also I only remember. Now, it just struck me, I don't remember. The other two constructions which you haven't spelled out, are they basically just variations of the first one? Like, if I chose
one
of F,
one of them feels like a variation. There is something which uses this linear feedback shift register business. Yeah, it's but that also feels a lot like that. You're multiply by something and then go mod, multiply by something, go mod. So the second, the whatever linear feedback shift register looks very similar to this. But the third
basically bounds what
similarly, basically you say that there is a dot product that is happening, and but the third construction that uses these character sum estimates.
Oh, right.
Yeah. So that's a very different thing.
This is what I am very different.
Yeah.
It uses some very advanced character sum.
Right. So that part is not complete. I mean, like at some point you will have to refer to something that says, no, we know these things happen. Yeah. Yeah. So those are the three constructions in AGHP. Okay. So then we will meet on Thursday, and I'll give some few more applications of epsilon bias cases.